So this figure then summarizes the antibody immune response. In fact, the title re-emphasizes the fact that this is still T cell dependent. So the role of T cells in the antibody immune response is again to activate B cells to form clones, which then differentiate into plasma cells. But let's start at the top, at the beginning here. Again, assuming we have some sort of infection which has resulted in an antigen presenting cell, like a dendritic cell or phagocyte, whatever you choose. The antigen gets, again, intracellularly processed, presented on MHC2 for recognition by a T cell whose T cell receptor is complementary to that same epitope. Again, the T cell here, sometimes called a CD4 cell because of the receptor that stabilizes the interaction at this immunological synapse. Don't worry about these other proteins for our discussion, but again, they're specific to the cells on which they're found. So this is the situation. We have one antigen and one particular T cell that becomes activated by binding, okay, of that epitope. What happens then? Well, only this one particular T helper cell gets activated and differentiates into clones, which will be producing cytokines such as this interleukin. Remember, some other place at the same time, there may be some immature B cells, and one of them here, you're having an MHC protein which is presenting that same antigen, can then react with the complementary T helper cell. So as those come together, the T helper cell, having already been activated, now knows to stimulate this corresponding B cell to produce more of itself. So here's the clone population, and then to differentiate into the cells that actively produce the antibodies. And you can tell now here's the IgMs made first, followed by IgGs, which peak a few days later. Remember, a subpopulation always differentiates into memory cells. These are not involved in that acute infection, but remain in the body in case of re-exposure to whatever pathogen those B cell receptors are complementary to. So again, just kind of take a look and appreciate the differences between the T cell interactions between the MHC2 on the original antigen presenting cell and the similar situation here on this B cell. And all these being B cell receptors, right? Not antibodies. Now would be a good time also then to review the corresponding animation in your mastering. So we're going to wrap this up here with looking at the kind of timeline by which the plasma cells are producing the antibodies. So again, plasma cell referring not really to the fact that they're found in the plasma, but a specific term to refer to the antibody producing B cells. So to remind you, now these produce both the IgM and the IgG using these extensive intracellular membranes, and these are the majority of cells produced during B cell proliferation, only a small percentage being the memory cells. The antibodies they secrete are all complementary to the specific antigen, but let's take a look at this timeline here. Some of the antibodies, the ones produced first, takes about 3 days though for this to get off the ground. IgM, those pentameric, those large ones that interact with the complement system, are produced first, and it's really about day 15 by the time we get an appreciable peak in the IgGs. So if we were doing this in lecture, I might ask you, what do you think this means with respect to how vaccines work? And why, for example, if you get a vaccine, say the flu vaccine, why you're not protected as soon as the next day. Well, the answer really is that the vaccine works by inducing a specific immune response, which then can protect you specifically upon re-exposure. But you'll note it can take up to 2 weeks to get an appreciable amount of that IgG made. So the plasma cells really don't last for very long. They die within a few days of being activated. The antibodies, as we've seen, though, can persist for quite a bit longer, and the memory cells for months or years. So this concept of immunological memory is really due to those memory cells that last beyond the period of the time of the initial infection. So these memory cells are produced by B cell proliferation, but again do not secrete antibodies at that time, but their B cell receptors are still complementary, match exactly the epitope on the B cell receptor. So the memory cells have the B cell receptors complementary to whatever it was that stimulated the original proliferation of the progenitor B cell. So these are long-lived, they persist in the lymphoid tissue, and will initiate the antibody production immediately if the antigen shows up again. And it's really obvious if you look at this graph here, where we have, in this case, a secondary response, where if there's a repeat exposure, because if you look at the slide, let's just go back here, say this was an inoculation or vaccination with a tetanus toxoid. Okay, so initially you see the IgM followed by the IgG. In this case, upon re-exposure to the tetanus toxin, we still get a little bit of an IgM response, but simultaneously and much more pronounced is the IgG response. So you can see this provides much more immediate protection the second time around compared to the first exposure. And just to reiterate, this rapid activation then of the memory B cells is really the basis for how vaccines and immunizations work. So, I mean, I'm really impressed. There's still about 2 or 3 more, let's see, of these animations that you can view. One on the primary immune response to detail that a little bit better, and on the secondary immune response. And then we'll end with the big picture. So go ahead and look at this one as well, and hopefully that will help tie together, provide just a summary of what we've covered in lecture the last couple days. With respect to some of these thinking questions, you might ask yourself why plasma cells are vital for protection against an active infection, but memory cells are not. Well, we're going to wrap up this chapter now with just a quick comparison of the different types of acquired immunity. Some of these are probably terms you've heard before, such as passive versus active immunity. So just to clarify what these terms mean, active immunity, this really represents most of what we've talked about today. Again, where a person, in this case a child, looks like he acquired chicken pox, his body will actively develop immunity to protect him during future infections. So this is a normal or natural process. Another normal or natural process by which people can acquire immunity is, in this case, the baby who is acquiring antibodies either from across the placenta, and those would be those IgGs, or here while the infant is nursing, it's present in the breast milk, and this would be secretory IgA antibodies. So the baby's not producing those antibodies himself or herself, but is instead passively acquiring those from the mother. But these are just both natural processes. Artificially acquired immunity really has to do with ways in which people acquire immunity with the help of medical or artificial interventions. The most common obvious example of this is vaccination. Of course, they can be either oral. In this case, this child may be receiving a polio vaccine, or by immunization through shots, or in this case, in some cases, One example would be if somebody's bitten by a rabid animal or bitten by a snake. So if there's reason in which immunoglobulins or antitoxins have to be rapidly administered, that can be done so to rapidly protect the individual. So again, in this case, the individual, this girl here, is not producing her own antibodies or own antitoxins, but is again receiving those preformed. So that's a passive acquisition. So that wraps it up for this chapter. Last question you may want to consider is, why is passive immunity effective more quickly than active immunity? And that is it. Thank you for your patience, and we will see you Monday.